might be
from the
bad.
rest of us. So.
Oh, remember, Forrest?
Oh,
Forrest.
And where'd he go?
I'm sure.
Forrest, yes.
Where'd Forrest go?
Sugar.
Forrest went to AB.
He's an AB. All right. So that's essentially what this Lagrange error bound is all about. Basically acknowledging that what we're doing is going to be an estimate, it's going to be off, and we're just going to try to put a cap on how far off we are. So yesterday, you all got terrified with all the notation stuff. Today, we're going to try to take the terrified stuff and bring it down a little bit so it's not quite so scary. So we're going to do 3 examples today, and I think we will, in all likelihood, probably take the whole period for those 3 examples. I do want to let you know that on Monday, you guys are going to want to have completed the intro video for Power Series. That's on your Schoology, it's on your Edpuzzle, it's on your calendar for Monday. So check out that Power Series intro video. Anyhow, so example number 1 says the first 4, look at this. It even just gives you the Power Series right here. It gives you the Maclaurin polynomial. It says the first 4 terms of this Maclaurin polynomial for each of the x are given by p of x. Says use Taylor's theorem to approximate e to the point 1 using that polynomial. So any guesses on what that would involve?
Error bound.
Oh, no, we haven't talked about any error bound yet. I'm only talking about
A tangent curve.
the first part. Well, let's try this again.
So,
All right.
we'll say,
No, hang on. We already have the tangent curve. Tangent curve is the p of x.
Are you just going to plug point 1 into
You're just going to plug 0.1 in. That's right. So we are going to say that e to the 0.1 is approximately equal to p of 0.1. And p of 0.1 being the tangent curve, if you will. It's the Maclaurin polynomial. And p of 0.1 for our polynomial would equal 1 plus 0.1 plus 0.1 squared over 2 factorial plus 0.1 cubed over 3 factorial. So all that we're really doing here is we're saying, hey, this polynomial is our approximation for e to the x, and this is our best approximation for e to the 0.1. That make sense? Okay. So I'll tell you what, let's just run it through the calculator real quick. Let's figure out what this is exactly. And we're going to do a couple things with this. This particular function is very convenient. So we'll kind of illustrate how this works and then do a little comparing. So please do figure out what this is exactly, or at least to 3 decimals or something like that. Let's do a lot of decimals because I think it's going to be pretty close. 1.1. I'm going to say it's like 1.2. ... That's my guess. Maybe not even. 1.1.
I got 1.105.
Okay. 1.10. Let's keep going. 105.
1666667.
Okay, so it might be 6 repeating potentially, maybe. Okay.
You missed a 6.
Oh, there's one more 6?
Yeah.
3 6s, then a 7. I missed it.
4 6.
Okay. So then the question would be, we know that is not exactly e to the 0.1. The rest of the question goes on to say, and show that the maximum error for this approximation is less than 5 times 10 to the negative 6th. That's the hard part. Yeah, what we just did there, that's definitely the easy part. So here's what we're going to do. We are going to say that the absolute value of e to the 0.1 minus p of 0.1 is the thing we're going to focus on, because what is that? That's the remainder, also known as the error. Okay, so the error that we're going to find here is expressed by the actual value minus our approximated value. And this is less than or equal to, and if you remember at the very end of our class yesterday, I said something along the lines of, 2/3 of this Lagrange error bound is just a formula. I just got done subbing for a geometry class in which they were finding areas of like parallelograms and rhombi and rectangles and all regular polygons, stuff like that. And let's just be honest. Like, if you know the formula, you just go plug, arithmetic, done, right? I'm hoping that as long as you guys knew what to do, that process would not be that difficult for you. Honestly, 2/3 of this is that. Okay? So let's talk about the really easy stuff first. So the first really easy part would be the x minus c. So what would you guys say is the x in this case? 0.1, right? That's the number we plugged in. That's the number we're trying to approximate at. Minus, what's my c value?
0.
It's Maclaurin, so the centering value is 0. So 0.1 minus 0 to the n plus 1. Well, what's the n? Like, where did we stop our polynomial? No, I stopped at degree 3.
Should be 4.
So 3 plus 1 is 4.
Over 4 factorial.
Over, and those two should match. That's exactly right. Over 4 factorial, right? N plus 1 factorial. And so that's the part that's just totally formulaic, right? You just go plug it in, done. Then we have this other part. Max value of the n plus 1th derivative at z. And this is where, like I said, you're going to have to use a variety of strategies and thought processes to get there. I think this is a very convenient one for us to start with, because what is the function that we would be finding the derivative of to get the subsequent terms? And what's the derivative, regardless of degree, of e to the x? Okay, so we're looking for the max value. I'll write this in. I'll write this in and then I'll erase it and we'll fill it in with better details here. So we're looking for the max value of the 4th derivative of f. And remember that z is just some number between 0 and 0.1. So we didn't want to use an x, we didn't want to use a c because those have other assignments. The z is just some number on that interval from 0.1 to 0, or 0 to 0.1. Okay, so let's think this over. So the 4th derivative, we know the 4th derivative, and I'll just scratch some thoughts down here. We know that the 4th derivative of x is equal to e to the x, like you said. So I want you to think about the graph a little bit. Can you guys identify any like really important distinguishing characteristics about the graph of e to the x? Horizontal asymptote. Yep, exactly. What else? Picture that graph. What else is happening?
It passes through 1 at 0.
0, 1. And it goes through 0, 1.
And it increases.
There it is. It increases, period, right? It's increasing the entire time. Now remember, we're looking for the maximum value of the 4th derivative. So if the 4th derivative, which is e to the x, if that is constantly or strictly increasing, where would its highest value be?
At the right end.
At the right edge, right? The right endpoint. So if you think about it, if e to the x looks like this, and you've got some interval in there, wouldn't the highest y value be on whatever the right endpoint is?
Yes.
Because it's strictly increasing. So here's what I would do. I'll erase this stuff down here maybe. I'll write some reasoning. I'll say because the 4th derivative is increasing on the interval from 0 to 0.1, the max value is,
When it says max, is that the max y value or the max x value?
y. Yep. So the max value of this 4th derivative would have to be happening at 0.1. That make sense? So what I can do now is I can come up here. I'll give you just a second to write because I'll highlight something and then I'm going to erase it. What I can do here now is I can now replace this just sort of vague reasoning or vague thought of like, all right, we're looking for this max value of the 4th derivative. I can replace that now with this. Does that make sense? Can you also see how if all you did was just look at that answer, you'd be like, what in the world? Where did you come up with that? But remember, the first 2/3 of this are just like, can you plug it in? Please plug it in right. And then the other part, that's where you're going to have to do a little bit of thinking. And this is one example of the type of thinking. You'll look at some other types of thinkings here in a second. Let's go ahead and use the calculator here to figure out what this is. So please take 0.1 to the 4th, divide it by 4 factorial, and then multiply it by e to the 0.1. So please give that a shot. Let's get an actual number there. And make sure that it really is less than 5 times 10 to the negative 6th, which is, that in itself is a pretty tiny number. What'd you get?
4.605 times 10 to the negative 6.
4.605 times 10 to the negative 6th. And Nick, did you get the same thing?
I typed it in, so.
Okay. Well, if Peyton's right, then this barely squeezes by the 5 times 10 to the negative 6th
I did the
threshold. Okay.
Wow.
So, kind of interesting if you think about it. That's only 4 terms, right? 4 terms, and we're pretty close to the centering point still, right? 0 to 0.1 is obviously quite close. But even with 4 terms, I mean, let's be honest, 4.605 times 10 to the negative 6, that's a really tiny number, right? We're talking about, what, 4 10 millionths, 4.610 millionths off? It's a pretty small error. What if we didn't like that, though? What if we're like, yeah, it's still too much error? What would we do?
Add a few more terms.
Yeah, put some more terms on there and figure out what the error is and see if that's okay. Okay. Final thing I want you guys to do is this. Will you please, in your calculators, figure out what just e to the 0.1 is itself? E to the 0.1. And then once you figure out what that is, please subtract our approximation and see if the resulting number is less than even 4.605 times 10 to the negative 6th.
It's 4.25.
Ooh, close, right? But it's less, right? So remember what this is right here. This number, this Lagrange error bound, this is not your exact error. This is the maximum possible error. And we found out that the maximum possible error is 4.605 times 10 to the negative 6. And because of the nature of this question, we were actually able to find out the real error, which was slightly less than this. I wanted to go through this just to kind of prove to you in a small way at least that this works, right? We've bounded the error. So this would be where you would say, well, my approximation is this 1.105 number, and I know that at the most it's off by 0.5 zeros and then a 4605. We've bounded the error. Okay. You all seem pretty calm. Has some of like the terror from yesterday dissipated a little bit? I hope.
Yeah.
No? Is it worse, Sam?
It's just same.
It's the same. Okay. Well, let's
You
see.
gotta be tripping on the YouTube video.
Say again?
You gotta be tripping on the YouTube video.
I did?
I was
At the end, you mean?
everywhere.
Stressed out.
I was
Really?
just so like the formula part I understood, but I was just looking at it going, wow.
I know it's a lot. It's a lot to take in, right? You could, I mean, seriously, couldn't you terrify 9th graders with this? Like, hey, stare at this for a while.
You'll be doing this.
Scary. Hopefully now you can look at it and say, yeah, still challenging. Sam's still a little afraid, but maybe he'll get better. We'll see. Hey, would you guys take a look at number 2? I think number 2 is going to be a nice question for you because number 2 will allow you to practice the building of a Taylor polynomial again.
Whoa.
So we did this the last 2 days.
Oh my.
Think of this as another opportunity to build one of these. And then in B, we'll start to analyze what an error could look like. So please, for number 2, see if you can figure out the 3rd degree Taylor polynomial. So 3rd degree, who knows how many terms that will be? You'll find out in a second. Well, maybe. It might not be.
6.
17.
Probably not going to be 6. Right? 3rd degree just means the exponent will be 3. Right? What? Really? 3rd degree? Yeah.
Oh, that's what that means?
Yeah. It means blah, 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 x cubed. Now, some of the other ones we've done have said find the first 4 non-zero terms. That could end up being the 4th degree, it could end up being the 20th degree. We don't know. So here we know it's gonna be 3rd degree, we just don't know how many terms it's going to take to get there.
About x equals 0 means the center and point is 0.
Right. Yep.
Wait, so, would it always start with one
Yes,
then if
yeah.
it's,
Wouldn't what start with
Would-
1?
cause you're going with the exponent of 0 when you're starting with the degrees, or is it just, oh, no, I guess it wouldn't be.
Well, it's gonna be times 1. Remember, the first term is f of 0
Yeah.
times x to the 0. So
You.
f of 0 could be anything.
Okay, I gotcha.
X to the 0 is gonna be 1.
Yeah.
So it's gonna be whatever f of 0 is times 1. Nick, are you interested in joining these guys over here by any chance? You're welcome to if you
Are
want.
you lonely?
I know that Aiden is super mean,
I know. he might-
and Logan sometimes is,
I
but
Logan
suck.
smells weird.
You don't wanna sit next to a golfer.
I'm like actually like concerned, cause I just came out
You'll
of
like
nowhere.
fall, you'll like fall down the stairs later.
Yeah.
oh,
That was the
come on.
weirdest thing, so now I'm like, do I smell bad?
No,
Guys?
I just say that
I
because
don't think
anytime
so.
anyone
Oh,
does
that-
it,
even
I
after we
have
played
never-
basketball.
I have never smelled you personally, Logan. I'm sure
You
you
wanna
smell
know-
great.
You wanna know how you know somebody smells terrible,
Like,
like
for my
just
adventure
naturally,
ones,
like if
yeah.
they don't do anything to fix it? If they keep deodorant in their backpack. That's how you know that they're always ready in case they smell terrible, because they know it's.
Yeah, those are good people.
Which is why.
Well, they're smart. They're
They're
prepared,
considerate.
right?
And
They're
you
very
know,
considerate.
I keep perfume
What's
in
that
my
in your
backpack.
Jack reaches in to get
I
his
do that on
deodorant.
days that I work out in the
Well, I keep
Yeah.
deodorant in my dance backpack for, because you know how we have dance in the middle
Yeah.
of the day.
Nancy's usually, sweaty.
No, this is dangerous territory. All right, let's see.
You
Let's
get sweaty, Jack.
Yeah.
let's
Fun
do
smell.
let's do the easy stuff.
Yeah,
Let's
that's
make
why
a table
deodorant
call.
in my dance backpack.
Instead of
Well,
like,
let's do the easy stuff.
it is easy compared to trying to figure out how to say that someone does or doesn't smell bad.
I should probably do this.
Wait, so the first is.
Oh, wow,
I'm
that's
part of
fun.
Wow, these numbers just get big.
I'm just gonna keep taking derivatives since this.
In other words, they do get large, but not
Yeah.
incredibly large.
They get more, in my opinion.
So as you can all see, this is from 2004 BC6. So believe it or not, this question was not calculator active. So number 6 is always no
It's
calculator.
5 times 125.
So consider.
600.
I guess you could be thankful if it's a sine or cosine.
That's going to actually be a key here. It's going to be really important.
It's really helpful when you just get into general because you can always rely that it's gonna be either sine or cosine.
Yeah.
And you can just calculate what it actually is.
It's going to be even more helpful coming up on part B. So recognizing kind of the nature of that graph is important.
They're both root 2 over 2, right?
Say again?
Cool, thanks. I was just asking that.
Well,
Love it
one
too,
over
Parker's.
root 2, because we're not in DC pre-calc anymore.
Oh, facts.
You don't have to flip anymore. I cannot tell you
I'm so new.
how many
Two.
points that I lost because of simplification. Yes.
My teammate is in Mr. Blake's class right now, and she just keeps missing stuff on her quiz, you know, for Mr. Blake reasons. And she goes, "Did you take DC pre-calc?" And I was like, "Yeah." And she was like, "This is the stupidest thing." And she was so mad because of how many like just random points she lost. And then her mom called me and she goes, "What did you get in DC pre-calc?" And I was like, "Michelle, I did really bad in DC pre-calc." And she was like, "So it's okay that Delaney's doing bad?" And I was like, "Yeah, it's perfectly
I
fine."
love Delaney.
I love
Good to know
Delaney.
you're the standard, right? If Peyton does bad, well, it's okay.
No, okay, I told her, I got a 28% on a quiz, so don't worry about your
I
child
remember
who's
when that
getting
happened. You were
75.
crying that day. That was so funny.
He literally emailed me, he goes, "I'm concerned about you, maybe we should talk." And I was like, "Oh, Mr. Blake, I'm sorry."
Was it a bunch of nitpicky stuff, or did you just not know what you were doing?
I just did not know what I was doing.
I was gonna say 28.
That was the unit that I missed for nationals.
Okay.
That's always hard, and it was like the hardest unit of the year, was like proving the sigma stuff,
Ooh.
Yeah.
and like all the series stuff.
I should probably.
Proving that the next domino falls.
Yeah.
That was, I actually liked
Yeah, the domino one was actually a lot of fun.
It was fun, except for the fact that I missed half of it and then took a quiz and got a 28% on it.
Yeah.
Actually, okay, now that I'm This actually isn't nearly as bad.
Wait, what are we playing for X?
Wait,
I remember in my class, I was
So it's, the centering point is x equals 0, or c equals 0.
Right. We don't, when we're finding p, the third degree of p of x.
We're not going to plug anything yet for a.
Okay, so we leave it as polynomial.
Just leave it as one. Yep, exactly. Yep.
Life is good.
All right, so I'm going to start here, and we can discuss.
This wasn't calculated.
This is definitely not calculator active.
what?
What?
Yeah, because you can leave it in fraction form. It's not.
Yeah, just leave it rational.
That's right.
Shoot, wait.
I have a question. This is very important. I ran out of room right there on the right, and I just kind of like, I just like brought it down here. Well, I can use, if I like.
Did you put plus dot 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 or something?
No.
Yeah, I think you go plus dot 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 plus, and then the rest of it. That's fine.
Because it's like right here. Is that cool? That's cool.
That's fine. Yeah,
I like doing an arrow.
that works.
Cool.
Next time, don't start on the right side of the page and then go right.
Oh, I hate when I do
My
that.
F primes took up too much
Like,
space.
You have like an extra like.
You know, I've used my, I gotta admit, I've used my iPad so many times. And of course, I can do this with my iPad. As you all know, I can pick something up and I can move it around.
Have you ever done that on real paper?
I've tried to do it on paper a few times. Yeah, I'd be like, oh, I don't like where that is. Can't do it. Yep, it's really rough.
I've had friends reach for the stick shifts in a golf cart before and like try to turn their turn signal on. It's really
Oh, I
fun to
do
watch. I'm
that.
just like grabbing nothing. Just
So I frequently switch cars with my mom because she has to take mine to work because she doesn't want to show up in a Mercedes to her client meetings. So sometimes I take her car to school and her like park reverse thing is up on the steering wheel and then mine is down like, where a normal one would be. So I get in her car and I'm like, and then I'll get back in mine and I'm like,
yup.
it's really difficult.
These are some major first world problems.
Aren't
Yeah,
they?
this is.
Yeah, you have to like reach up there instead of here.
I know.
Change gears.
It
It's really
is
just,
a
like,
real
talking
problem.
about human habits.
Hey, you guys agree with my first two terms up there?
Why would she plus pi over 4? Oh my gosh. I did the whole thing wrong.
I was like, wait, I definitely. That hurts your voice to do it.
That hurts my ears.
Imagine being right next to it.
Imagine being stupid.
I can.
Nick, I didn't do math right.
I totally forgot. Oh shoot.
I forgot how to do basic derivatives.
Okay, so now we gotta, oh shoot, we have to figure out the math.
Yeah, I just got to that step too.
I got to that step too, but then I realized I don't know how to do a basic derivative, so
So cool.
I'll put that down. Mr. Anderson.
Is this looking okay still?
Yeah. This is the location of the max.
I mixed that up.
So.
Let's not worry about B yet.
What?
Remember, this is no calculator,
Yeah,
so
I'm using it.
yeah, don't be pulling the calculator out or anything like that.
Yeah, what's 125 times 5?
625?
625.
What?
No, wait.
That's cosine.
Oh, oh my god, we have to do critical points.
This is a major.
So we have to do.
There's a reason he told us the 3 examples we're going to take this entire period, guys.
Yeah, we're not going to be done with this in 4 minutes. So I have what I think up there is a good solution for the Taylor polynomial, third degree.
Mr. Anderson, I didn't even know how to do derivatives.
Well, this is probably a good
How
reason
am
for
I
us to
in
be
this
doing this. It'll
class?
remind you. Thankfully, this was not like the final exam today. You have a chance to learn a little bit, remember, and remind yourself.
But the derivative of.
Okay, so do you guys have any questions on how I've constructed that? Or how
No.
you've constructed that? So then, let's take a peek at B then. B says use the Lagrange error bound to show that, and I want to highlight this, what on earth is that?
That's
That's
just
the error.
That's the error, right? So it's really important that we recognize what that is. So we're wanting to make sure that the error is less than 1/100th. And we can interpret a few other things about this. First of all, we know that our C is 0, but what's the X value that we would be plugging in here to find some approximate value?
1-1.
1/10, yeah, 0.1, okay. You can see that in both pieces on the error. Okay, so here's how I would start. I would say that f of 1/10 minus p of 1/10 is less than or equal to. So remember the first 2/3 of this, see Tyler? First 2/3 of this are completely formulaic, and just plug it in, and you're done. So it's x minus c is the first part. So what's my x value? It's 1/10, yep. Minus c, what's my c?
0.
0. To the n plus 1, so what is n?
The fourth.
3.
N is 3, so n plus 1 is 4. Good, so this is similar to the other one in that respect. Divided by?
4 factorial.
So please understand, that part is just, can you plug a couple of things in, and you're good.
And then there's the part.
And there's the other part, that's right. Okay, so I want to remind you something that Logan said a couple minutes ago. He said, it's really convenient that it's sines and cosines. And I agreed with him, and I think that it's even more convenient than you might have thought, because when we think about it's going to be the max value of the fourth derivative on the interval from 0 to 1/10, right? So what is so convenient about this? Well, I want you to think about the graph of, let's see here, the third derivative was cosine, so the fourth derivative would involve sine, would it not? I want you to picture that graph of sine. Can you see it in your mind, like roughly what it looks like? We all remember, I mean, just like a really basic version of sine. Okay, so I don't want you to get too hung up on the specifics here. I just want you to think about sine, the parent graph of sine.
Increasing.
What's the maximum value of sine? 1. Okay. So then we got to now be a little more specific to this one. My third derivative was negative 125 cosine of 5x plus pi over 4. So what is my fourth derivative?
625 sine.
Yeah, 625 sine. Yeah, you got it. Okay, so this is a representative of the fourth derivative. And listen, we know that this 625 sine of blah, 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 this could take on a lot of different values, couldn't it?
Yeah.
Between 0 and 1/10. And I mean, there's no calculator here. And so, we're a little bit in the dark as to what's going on here. But what I want you to start to think about is, all we're trying to do is bound the error, right? So I want you to think, what really is the maximum conceivable error of that fourth derivative, value of that fourth derivative?
625.
Is it? Yeah, 625. That's the highest it could possibly be.
But don't we have to do it within our interval?
Well, we don't know. From 0 to 0.1, we don't know exactly what it is, but I can tell you this. It's less than 625. Does that make sense?
So it's definitely less than 625.
For sure. Yeah, you could say, well, I think it's only 10, and I'm like, I don't know, maybe it is, maybe it isn't. Or I think it's 400, I don't know, maybe. But you know what I can for sure say? It's less than 625. Does that make sense?
So we got plug
So
in
is that
625.
all we need to do?
So let's try it. Let's see if that works. So what you want to do here is you want to find the value that you can give a reason for. So think about it like this. If I just put yourself in your own shoes for a second and say, what if Mr. Anderson put 5 right there? And you said, why did you put 5? And I said, well, I thought that seemed reasonable. Like if you're really being honest about it, you'd say, come on, that makes no sense. How could you just say that 5 seems reasonable? And what if I put, 20? And you said, why'd you put 20? And I'm like, I don't know, I figured that had to be about where it was. Like, that's ridiculous, right? But if I put this up here and I said, you know what? I'm going to put 625 right there. And you said, why? And I said, I know, based on my knowledge of sine graphs, that the highest that thing could be is 625. You really can't argue with that, can you?
No.
You can say, well, I think it's less than that. And I'll say, well, I agree with you, probably. I don't know how far less it is, but I agree that it's got to be less than that. Does that make sense? If there's no calculator, isn't that about the best you can defend? You really can't defend anything else.
You can take another derivative and then find critical
Maximize
points and
it.
then find the actual max.
Yeah, but I'm trying to take you to a place like on number 3. I'm trying to take you to a place on number 3 where that's not even possible. Does that make sense?
Mr. Anderson,
Yes.
how do we show that we know that? Like,
You really,
the exam.
I would be fine if you
an
just wrote
AP
625.
reader was reading it,
Yeah, they'd give you full credit. In fact, they'd be looking for that value. They'd say, oh, I sure hope she put 625. Yep, she
I
did.
don't have to write like
good.
the
If you did
maximum
it though, like,
value
would
of
you,
No.
this.
would you do
Okay.
the fifth
Nope.
derivative to get?
Aiden, question?
Yeah, you do that.
Um,
I did it all wrong.
I think we just, never mind.
So, for some folks, one of the most terrifying things is what comes next. So, check this out. We got to do a little arithmetic to prove that this is really less than 1/100th. Because right now you can't. I mean, seriously, if you look at that and you say, "Well, duh, of course that's less than 1/100th." I don't think you know that.
That's one.
Right?
Oh, that's a really, really,
One
really small
1,000,
fraction.
1,000.
So let's think this over. So it's 1/10,000th.
Over.
Yeah, 1/10,000th over 4 factorial times 625. Now I'm going to pull a jack and come
Nice.
over there.
But it wasn't, but no, it'd be like 1/10,000 over 4 factorial, then it's the arrow, then it's times.
So let's see here. 4 factorial is 4 times 3 times 2 times 1.
24.
So it's 24. So it's 625 over 24,000, right?
No, 240,000.
Or two. Oh yeah, 240,000. Yeah, you're right.
Yeah.
Did you say 24,000, Peyton? I thought I heard you say
That
24.
was you?
I thought you said 24. That's what I wrote down.
Oh, well, I
It's
said
okay.
24 as in 4
It-
factorial is 24.
So let's think this over. We can reduce by a factor of 5 for sure, right? So what's 625 divided by 5?
125.
Okay, what's 240,000 divided by 5?
48,000.
48,000. This is still, we're not quite there yet, but we could still keep dividing by 5, right?
Yeah.
So this would give us now 25. 48,000 divided by 5?
No, I can do it. Don't say it. No. No.
Couldn't you just
9,600.
Dang it.
We could, by the way, we could have done this reducing earlier than later.
125?
Say again?
Can you just divide?
You could, if you could see it, that just divide everything by 125, that would work too. Yep. And then this would equal finally 5 over, what is 9,600 divided by 5?
192.
192?
No.
No.
Or 1,920.
1920, believe it, yep. Wait,
No, still no.
Yeah?
Yeah, it is.
so 500, 4,500. Yeah, it is, it's 1920, yep.
Yeah, it is.
That's right.
Yeah.
Okay, and then finally, what is 5 divided, or what is 1920 divided by 5?
I don't know, it ain't 100. It's bigger than 100. I don't know that much.
Right.
384.
Yeah, it's just.
Say again?
384.
384, yep. Okay, so 384, and that is less than 1/100th. Sorry, I kind of ran out of room there up against the hand. So nobody really shouted me down on this, so I didn't do anything. Couldn't I have done all this reducing here before I multiplied by 4
Yeah,
factorial in the
probably.
denominator? We could have done a bunch of canceling there. Probably would have been a little bit easier to cancel the 5s out of 10,000
Yeah.
rather than 240,000. So you can always do your cancelings earlier if you see them. But the finished product with these will always be something like that. We've proven that the error is less than 1/100, so we're done. What do y'all think?
I mean, I think the arithmetic is harder than the actual.
Oh, we're making progress. Are we making progress on the?
Because arithmetic
Being
is
terrorized?
hard.
No, we're making progress because yesterday when you looked at the Lagrange error bound, you thought, I can't do that.
Yeah.
And now you're saying, well, I can definitely do that, but now the arithmetic is bothering me.
It's just the max part that's still
Okay.
stressful.
Sam, any better?
A little bit.
A little bit? Okay. Oh, you're holding on to that very tightly.
I'm not gonna, like, if I'm in the test, I don't think I would have seen that 625 part.
Yeah.
And that would have taken me forever to do it.
I would have been in the fifth.
Thankfully, this is not the test. You're just like trying to build.
You know what's the funny
And
part?
build? What's
Is
the
if-
funny part?
If you did the 625 thing and it was bigger, then you'd have to take the derivative.
You know what? So you're going to be. Can I just completely let the cat out of the bag? You're going to be set up for success. Like it's not going to be. Oh, gee, Jack, if only you had guessed 49.316 pi. You know, it's going to be like the numbers are going to be like very accessible. So if you find yourself like, overcomplicating it and be like, oh, I should have guessed 3.92. Is that going to work? No. 3.918? That didn't work. You probably made a mistake somewhere. You should go back and double check your work, because it's not going to be a guessing game where if you would have only guessed out to the 20th digit, you're good. It's going to be, how about pick an integer value like 625?
I think there would be a way to actually find where that maximum is if the maximum is on the interval or not, because
Oh, there is a way on that one.
yeah.
But look at number 3. So I was like trying to help you guys build towards number 3. All that reasoning's not going to work here on number 3. Okay. So check it out. It says the 5th degree Taylor polynomial for some completely unknown function g of x. We don't have a clue what it is. And this is a little bit more realistic. Usually these Taylor polynomials come out in real world examples, and we have to deal with them, and we don't even really know what the function was that made this. We're just going to call it g of x. So this 5th degree Taylor polynomial is up there. It says the graph of the 6th derivative of g is shown below. So part A says use the 5th degree Taylor polynomial for g of x about x equals 0 to estimate g of 1. So can anybody, like in your own words, explain what A is wanting us to do?
Plug in numbers.
Yay, plug in a 1, specifically a 1, and that's it. So for A, we're going to go I'll say g of 1 is approximately equal to p of 1, and we just plug in a 1. Yeah, that's fine. The common denominator, I think, probably is 3,600. We could obviously work out what exactly that is, but I'm not.
5451.
Say again?
5451 over 3600.
All right, let's do it.
You know what?
5451 over 3,600. Take that, Julia, Megan, Santi. Logan has it. Okay. And Aiden, you said you thought that was correct as well?
No, I was going through the mental math, and then you said it. And
You were almost there.
Yeah,
Okay.
I was getting there.
Okay, so then B says, explain why your estimate in A differs from the actual value of g of 1 by less than 1/100th. Okay, so let's think about the wording here, right? Because Sam, you were talking about this earlier. This is important to think about. You're like, man, I'm not even sure if I could come up with the 625 thing. Like, make sure that you understand this wording, why your estimate differs from. When you see the words differs from, what are we talking about?
Error.
Error. That's right. So it's asking us to bound the error, right? Like, is the error really less than 1/100th? So I would write this. G of 1 minus P of 1 is less than or equal to. So the error is bounded by, and the first part, remember, is just a formula. Plug stuff in. So the first one is x. The first piece is x. What is your x value here?
1.
It's 1, yeah. Minus the centering point? 0. To the what power?
6 factorial.
To the sixth power.
It's to the 6 factorial, really, Logan.
Well,
It's over 6
Over 6 factorial. I think we all knew where you were going with that one. So guys, that of course
No matter what it's to.
that of course is the part
again.
that is, that's the part that's just a formula. The next part is the part you're going to have to do a little bit of thinking. Remember, it's the max value of the n plus 1th derivative, and since n is 5, this would be the max value of the 6th derivative. Or sorry, it's not an f, it's a g. So where on earth are we supposed to figure out anything about the 6th derivative?
The graph.
You have a graph of it, right?
And the maximum
So
value is
Sam,
6.
listen, Sam, to maybe alleviate any concern you might have, you're going to be set up for success. Like if I give you a graph of a 6th derivative, you got to think, I might use that. And if you find yourself not using it,
It's definitely going to be below 6.
perhaps you should consider maybe there was a mistake made. Okay, so Peyton says what for the max value?
6.
You think it's going to be less than 6? All right.
And Logan says I'm wrong. Tell
So-
Logan I'm right.
No. It was a misunderstanding.
Thank you.
So if I draw a little dotted line over here from that y value of 6, can you see how it's really hard to say, like between 0 and 1. What's the max value? Is it 5.2? I don't know.
Let's just go with 6.
5.3? Go with like the most easily defended logical value you can find, which is 6, right? So I'll erase this max value of the sixth derivative, and I will just put times 6. Now let's see what happens. I think you're going to find the canceling and simplifying here to be quite a bit easier,
Really nice.
right? So it's 1 over 6 times 5 factorial times 6. Do you see how the 6's just cancel off the front there? Okay, so what is 5 factorial?
120.
120.
Bigger than 100.
Yep. So it's 1 over 120, which is indeed less than our target error of 1
When it comes to
100.
those equal signs, because you do like g of 1 minus p sub 5 of 1
Yep.
is less than or equals that.
So the error, all I'm saying is I'm saying that this equals that, equals that, which equals that. And that's all true.
Right. But does it make a difference that you have that less than or equal sign over there? 'Cause
As opposed to,
Aren't you equating g of 1 minus p sub 5 of 1 equal to that?
less than or equal to.
So it would be a problem if you said like just equal, just less.
Yeah, if you just said equals, if you made this an equal sign, that's a problem, because then you're telling me the error is exactly this. Lagrange error bound is just going to put a bound on the error, say that it can't be more than this, so it's got to be less than. Realistically, it's almost always just going to be less than.
It's more of a
So-
it's more of a notation thing. Like I was just curious. So
Yeah.
be
Yeah, I was
confused.
asking about.
So bound. So think about it. The word's bounded by. Like, so if I said, Jack, I want you to go get pizzas for everybody. Here's $100. Aren't you? Unless you have extra money, aren't you bounded by the $100? So you can spend up to and including $100.
You'd spend
So I'm just saying that's a lot of pizza, unless it's Bojo's, which would be nice.
Wait, can we do
So all it's saying here is that the error could be at most this.
Right, and that's not really. I was just asking about the notation thing, because like not like less than or equal to. It's just that. Does the, it's like
Does money really bound you?
you know the
You have a car?
if A equals B
You're
and
spending
B equals C, then A equals C.
Yeah.
I was just
Transitive property.
I was just like
techniques.
I was asking if it would be. I was asking if since that less
So
than
no.
sign was there, if it was a problem that we also
David
put an
Copperfield.
equal sign over there to the right.
No, I don't think it's a problem at all, because this equal sign right here is saying that this thing here and this thing here are equal, and they are. And of course, this equal sign is saying that that's equal to the other two orange boxes.
You don't need to get one.
So it's a left to right thing. It's not necessarily.
Yeah, I'm reading it from left to right. Yeah, I'm saying that this thing is less than this, and this is the same as this other thing, which is the same as this other thing, which is less than my target. So you really could read it like an English sentence, right? And say, well, this is at most this, which is the same as this, which is the same as this, which is the same as this, which is less than this other thing.
Oh, that'd be so good.
So yeah, I think it's good.
Like a month in, you will see.
Okay, hey, fear level yesterday,
Way down.
is it down here somewhere?
Yeah.
I don't know, less than up here.
I'm not sure it's that far down.
It's at least down to eye level.
Santi, Meg, and Julia are gonna have a time and a half watching that video.
They can still hear you.
Hi,
You wanna say
Santi,
hi
Meg,
to
and
them?
Julia.
There we go. Hey, have a great weekend, you guys. Don't forget the intro video for Monday, okay? Intro video for class on Monday on Power Series.
You're welcome.
Have a good weekend.
Me too.
Justin, have a good weekend, man. See ya.